Sir. Sir, Murli sir. Sir. Sir, now it is working, sir. No issues. Hello,
yeah,
sir.
Okay. I had some issues with the browser and it crashed, so I had to restart again the session. Now I see that's okay.
Hello.
Hello.
Yeah. Is it working?
Yeah, sir. It is working.
Yeah,
no
it's
issues.
okay, yeah.
Okay, sir. Alvin, sir.
Dr. Bhatt.
Okay, sir.
Yes,
okay.
yes, ma'am. Okay, just a minute. I will stop.
Yeah. Shall I share the screen right now?
Just wait for just 2 more minutes. By 6:30 we will start. We will start with a normal procedure. First, I will introduce you, and then you can share your screen, Dr. Bernat.
Okay.
Okay.
Okay, that's fine.
First,
Okay,
I will introduce you to our participants, and then you can start presenting. Okay.
புரியல sir.
That's great. Great.
And
ஒரு காவலியா பாருங்க
just 2 more minutes.
வருதுங்களா ஏன்னா இப்பதான் எனக்கு வர்க் ஆயிருக்கு அப்பனா 30 செகண்ட்ஸ் உங்களுக்கு ஒரு 1 or 2 மினிட்ஸ் டிலே ஆகும்ல அதனால ஓகேவா ஓகே சார் இது இஷ்யூஸ்னா சொல்லுங்க ஓகே சார் ஓகே थैंक यू சார்
We will start exactly by 6:30. So 4 more minutes here. Hello. Good evening. Yeah. So good evening, everyone. We will start the webinar now. So I request before starting, I request all the participants to mute your mic and then switch off your video, please. So you can switch off your video also, so that the bandwidth will be fine. Okay. So again, good evening all. So we will start at the outset. I welcome you all the participants at this evening moment for this international webinar series on nanomagnetism. I like to thank our speakers, Dr. Bernat and then Dr. Ponpandian, for accepting our invitation to give a presentation on this webinar series. So, nanomagnetism is a recent field, which comes in all the branches of science. Nanomagnetism is applied in bio, in physics, in chemistry, in all the branches of science. So, we felt that this will be a very good topic to learn, and we have two experts here. Dr. Bernat, he started his career in the year 2003, measuring magnetic properties. Okay, I know Dr. Bernat right from 2007 when I joined as a postdoctoral fellow in ICMAB, Barcelona. So he was working with at that time 3 ppms, I think, with 1 mpms. So he has a very good expertise in measuring the magnetism, and measuring magnetism is especially the nanomagnetic material. Measuring the properties of a nanomagnetism is very difficult. So we need to follow certain categories. So for that, we were so happy that Dr. Bernat has accepted our invitation immediately and ready to give this presentation. Okay, thank you, Dr. Bernat. And I like to thank our college management, our principal, dean, and our faculty members, Department of Science and Humanities faculties, especially physics and chemistry faculties. Because without their teamwork, without their efforts, this webinar would not have been possible. So I thank them all for their efforts. And then I hope people will all the participants. There was an enormous response here. Almost we have received 800 participants. 800 participants. Unfortunately, we could admit only 100 in the streaming is going live on YouTube also. Okay, so the others, other participants, they are watching on the YouTube. Okay. So if the participants have doubts, I request the participants at the end of the presentation, you can type your doubts on the chat box. Okay, our speaker, Dr. Bernat, will read that and then we'll answer that. He will be very happy to answer all your doubts. Okay. So thank you, Bernat. So now I will pass the mic to Dr. Bernat. So, Dr. Bernat.
Thank you very much, Dr. Marie. It's a pleasure to be here today to give this presentation to this audience so far from my home. It's something that is quite special for me. So my purpose today is to give you some ideas on how what's behind the magic of obtaining the magical properties of the materials we want to study. That includes protein nanomaterials, which is something that is very trendy nowadays. So basically on my speech will cover just more the proof of concept thing and less on the more technical details. So before starting, I would like to give you some clues about the place where I'm working. So I'm working what we call the Institute of Chemistry Materials of Barcelona, which we are located in the zone nearby the Barcelona city. It's an image of the building. So basically, we are focused on material science research, and that includes these 5 research lines. That includes sustainable energy convention and storage systems. That includes also superconductivity, some electronics and the scope of oxide electronics and molecular electronics. And finally, we are also working with some aspects of the biomedicine. So these 5 research lines are carried out by several research units, which cover either one or more than one of the research lines. That includes the superconducting group, theory and simulation, molecular and supermolecular materials, solid-state chemistry, magnetic materials and oxide, functional oxide, functional surfaces, embedded study and functional characterization, molecular nanoscience, and manufacturing materials for optoelectronics. All the research group usually need some kind of large lab facilities. These are some kind of expensive laboratories, and normally these facilities are shared for many of them. That's the main purpose of the existence of this scientific equipment platform. These are the shared lab facilities that include electron microscopy, clean room, thermal analysis facility, thin film lab, X-ray diffraction, spectroscopics, scanning microscopy, preparation or characterization of plasma materials. That is more mainly focused in the particle size estimation. It's a very powerful lab. And finally, the low temperatures and magnetometry laboratory. This is the one I'm responsible of at this moment. So basically, this lab provides service for ICMAB research lines as well as groups nearby, and they are devoted to the magnetic and electrical characterization of the materials being investigated. The lab is equipped by 2 NPMS XL magnetometers. These are developed as a detection system. Normally, a detection system consists of some search color or limiter. Basically, we have our system with a solenoid that produces a magnetic field. It magnetizes the sample. We have a sample placed on the center of all search coils, and we can measure the magnetization. Well, the most simple way would be to use what we call the extraction method. Okay, the extraction method relies on the effect of this electromagnetic force appearing at the search coil system that is proportional, as we said before, to the magnetic induction change. In order to properly measure the magnetization of our sample, we need to reject the external field effect. That is, if we fix the magnetic field and we make it steady in time, we are okay. So at the end, the effect of the signal generated at the radiometer is then proportional to the change of magnetization of our sample. So the extraction method would consist of placing first the sample inside our search coil system and firstly taking it out from the search coils. So the initial state will be that with the sample in, this magnetization, and once we have the sample far away from the search coil, we no longer measure its magnetization. So the magnetization out is 0. So this delta magnetization is directly the sample magnetization. Okay. We can now introduce another kind of magnetometer system, which is so-called the vibrating sample magnetometer. This was first introduced by Foner in 1959, and this is somehow more complex construction. but it has some advantages. Basically, we have, in this case, in the original setup, it consisted of an electromagnet, some pickup coils, and our sample at the end of a rod. This rod was connected to a loudspeaker, right? Okay, and thanks to this loudspeaker, a vibration was introduced. So we have this sample moving next to our detection system, and this caused the periods of a voltage, an alternating force at the search coil system, which was somehow proportional to the motion caused by the loudspeaker. Okay, so basically, although this will be also proportional to the magnetization of the sample. Okay, this signal is somehow unknown. We have to establish a relationship between generator voltage and the magnetization. This was carried out by the presence of a reference magnet, it's a known magnetization, and the identical construction of pickup coils. This would generate a known signal. So basically, the sample moment was determined by comparing the generator voltage at the detection coil and the generator voltage by the reference system, multiplied by the magnetization of the reference sample. We could get the magnetization of our sample. The advantages of this system is that it's a very fast measurement system, and it can also measure the sample magnetization asynchronously to the magnetic field change if you're using the appropriate radiometer system, and also has a very high, much higher sensitivity than that of the extraction method. Okay. So now let's move to an implementation of this BSM system. This is an explanation, small schema of the BSM system we have in our institute, which is called the PPMS BSM option. And basically, the construction of this setup is based on the funnel system, but it has some changes. For example, it substitutes the loudspeaker to a linear motor, like the one you see coil, constructed in a way that the vertical force that would move the motor up and down is proportional to the applied current. And there are some permanent magnets in there that generates this force. Okay? We don't have a reference sample in this case. We use a calibration. Basically, we calibrate the system with a no magnetization sample in a very controlled environment, condition of temperature and field, and with that, we can easily determine the sample volume. Okay. Sorry. Okay. So if we divide the voltage of the sample, we divide it to the calibration and the amplitude of the movement and the frequency, we get the magnetization. We have some electronics that controls the motion of the motor, and thanks to some locking techniques, we can extract a very pure, can filter out the signal coming from the signal we want to the noise we can have in our system. The sensitivity of this system is 10 to the minus 6 mu at low field. This kind of field can be up to 9 Tesla, 90 kilohertz, thanks to a near titanium superconducting scenario. System can work in two temperature ranges, from 1.8 Kelvin to 400 Kelvin, and from 300 Kelvin to 1000 Kelvin using a special sample folder, which includes a small filter. Okay. So, second example would be how we implement a squid sensor into a magnetometer. Basically, since a squid is so sensible detector device, is that in a normal system is not playing a direct implication on the sample magnetization measurement. It is placed inside a flux conversion flux transformer system. Basically, this is what we have here. We have our sample here in the second derivative detect an array. This electromagnetic force will generate some currents, which of the magnetometer. This is the image of the real magnetometer. This is the solenoid which we use for the magnetic field. In the center of the system, we have some sample space. Surrounding the sample space, we have the second order radiometer, okay, which is made of all of it is made of superconducting wiring, which is now very entitlement in all the construction. Okay, sample is placed in the end of the sample rod, so we can move it up and down. So this will cause this magnetic flux change in the solenoid, and will give us the signal that we can treat and determine the magnetization of the magnetic moment of the sample. Okay, this system, the solenoid is made of neodymium titanium and is able to apply 75, and the temperature control of the system is from 1.8 Kelvin to 400 Kelvin. Okay, so basically how we treat the signal of the sample through this second order radiometer by step-by-step motion, and at each step we take the discrete voltage. Basically, this gives us a voltage to position dependent curves like this one. So if the sample is far away from the radiometer, we will give no signal. As we approach to the bottom coil, it will give you our response system will give you a voltage. As we move forward and we approach the center coil, we'll have another peak, which is inversed in polarity, and normally, ideally, twice the value on the first peak. And as we move forward and we approach to the top coil, we'll get identical signal as the first coil. So once we get this curve, this is the curve expected for a point like dipole, which is second order radiometer. We can adjust this curve, and from that curve, we pick it accordingly. We can determine the magnetic moment value of our machine. Okay. Basically, we can plane the direction in two ways. What we call the DC, made of all of DC motion, which is this step-by-step motion that I now said. It has a single scale construction, and this has a sensitivity. A sample is placed minus by the end of the sample rod. However, this method is can move it quite slow and very sensitive to what cause this. Since a measurement like this takes solenoid, normally will give us a half a minute. You can treat if you have some electronic position, the voltage at the beginning, the voltage at the end. Is no longer the same. So the solenoid next to the solution that is able to apply 70. In order to overcome these limitations, we use what the temperature control of the system is from 1.8 Kelvin to motion. Basically, it's an oscillator. It's based on how we treat the second sample through this second radiometer. We get the discrete voltage measured, and at each step we take the discrete voltage motion. We improve the sensitivity to order of magnitude down to the 10 to the minus 7 MU in noise floor, and it is a faster measurement, basically because we have more voltage for taken during this measurement. We have a better noise rejection since we have more photons. Since the scan time is somehow effectively reduced the electronic problem. Now let's move to a conceptually different magnetometer, which is called the AC susceptometer. Basically, this AC susceptometer is interesting for investigating the magnetic response dynamics of our material. We are no longer keeping an external constant magnetic field. Probably we are applying a bias constant magnetic field, but now we change it over time. Most usually in a sinusoidal time-dependent way, okay, with a certain amplitude. Since we are changing the magnetic field, we change the magnetization of our material, we will respond in a similar way, okay, with a certain amplitude, and with the time dependence, it will be similar to the one of the magnetic field, except for a delay. In order to treat this delay, we need to separate the magnetic response into two contributions, basically, M prime and M2 prime, being M prime one response which is in phase with the applied magnetic field, and an out of phase which goes 90 degrees in delay with respect to the applied magnetic field. These two contributions have two meanings. The in phase computes you the local change of magnetic field of magnetism with respect to the applied field, and the out of phase contribution is related to losses. Normally, this is useful for detecting some magnetic phase change at a certain temperature, for example. This would cause when you have a phase change, we usually have some energy losses involved. So at the end, you have this delay effect that you can effectively measure. Basically, this time variable magnetism dependence would cause the generation of voltage at the surge coils that would be proportional to the manipulation of the sample if we do the proper calibration. Normally, since we are using time-dependent signals, we need some locking techniques to filter out the signal what we want with respect to the parasitic signals which disturb the accuracy of our measurements. So let me introduce now an implementation to our quantum design system where we have in our lab. Basically, this is a schema of the AC solenoid and the detection system. This is somehow a little bit more complex construction than the one I schematized before. Basically, you have in center a sample space. And the blue part is the AC generator solenoid. Okay. The red parts are the surge coils, which in this case is a first order limiter. Okay. We have some calibration coils which are used internally for giving a better accuracy of the generator signal, and some compensation coils that makes our system better performance when in the measurement. And at the top is the contact to electrode, and at the bottom is the contact to electrons. Basically, as I introduced before, the voltage at the core is treated with some locking techniques. In this case, we're using a software locking. And the specification of our system is that the amplitude of the applied AC field is 15 Hz. We can work in a frequency range from 10 Hz to 10 kHz. We can apply a biased DC field up to 90 kHz. The system has a sensibility of the M prime and 2 prime down to 2 to 10 to the minus 8 mu, and the working temperature go in the range of 1.8 Kelvin to 350 Kelvin. Okay. This sample is placed at the end of a sample rod, and the other side of the sample rod is a stepping motor, in which we can move the sample up and down for several reasons. First, to center the sample with respect to the millimeter, and secondly, to perform some kind of a more sophisticated measurement protocol, which makes our results more accurate. Basically, this measurement protocol is what we call a 5-step measurement. The first step would be to place sample at the top coil, apply the field, measure the position, then we place it at the bottom coil, we repeat the same, and the difference between one measurement and the other would let us evaluate the slightly difference we can have in the top and the bottom surge coil, which can be ideally not, but there could be. Sample at the center of the emitter, and we calibrate the amplitude and the phase using a good fake a magnetization signal. Again, finally, we place the sample at the top coil and repeat the phase measurements. With this, we reject the field in this long measurement. Okay. We have another implementation of AC subscriber. In this case, it's placed in one of our two MPMS systems. Basically, this is the schema I showed you before for the AC Magnetometer. But in this case, we have another superparamagnetic scale. Okay. So, in summary, today we have learned the following. We have learned several ways to produce a magnetic field with some examples and with their strong and weak points to each other. We have learned also how to measure the manipulation of the sample with several methods. We have also learned the working principle of several magnetometers. And finally, we have given you some examples and some of what information you can extract from magnetic measurements. And thank you very much for your attention.
Thank you. Thank you, Dr. Bernat. Thank you, Bernat. So now this is open for discussion. Now there are some questions on the chat box. So Dr. Bernat, can see some questions, general questions there. Participants, if you have any doubts on the presentation, you can just type on the chat box. The speaker, Dr. Bernat, will answer them. There are some questions on the chat box.
Now see the first question, if I'm not wrong, sir, is it possible to produce electricity in large for commercial use through magnetic fields or like hydropower? How does the magnetic field behave at cryogenic temperatures? Well, let me give you a little bit about the first question. Is it possible to produce electricity in large for commercial use of magnetic fields? Well, probably you are referring more to the in principle you could probably you are referring to the use of superconductivity in the production of electrical power. Is that right?
I think so. That's I think it's a general question. There are a few more questions at the bottom.
Let me answer the second one then. How does a magnetic field have a cryogenic temperature? Well, in principle, magnetic field itself should be independent of the temperature what it concerns to the production. It only depends, in the case of solenoids, it depends on the construction of your system and the current you apply. So basically, probably at low temperature, at low temperatures, your solenoid could be more performant than in high temperature. But it could be a big impact is on the use of superconducting solenoid. Then, of course, at room temperature, a superconducting solenoid is pretty useless. It has no effect. At cryogenic temperatures, then it makes a difference. You can apply, you can produce several Tesla. In that case, without the need of a huge power plant to produce electric. So, second question is it possible for wireless electricity using magnets? Using the North Pole to pole effect? Well, wireless electricity is somehow existing in electrical transformers. In fact, you are sending electrical power from one solenoid to the secondary solenoid. It's well, I know from with magnets. Well, as long as if you, for example, if you would move the magnet, if you are able to produce a time-dependent magnetic field, you can couple it with a solenoid. You can produce electricity with one kind of wireless production. But the key to that is you need a time-dependent magnetic field in order to produce electricity. And of course, you will need a solenoid for that. Next question. Very nice. Next question. Can you explain how to find the size of particles from temperature determined radiation data? Yeah, this is more or less what I explained before. Yeah, in order to determine the particle size, in this case, yeah, you have to previously know the anisotropic constant, which is part of this blocking temperature to volume dependence. Basically, if you had a single distribution of a particle volume, this blocking temperature should be unique. It should consist of a single peak. If you determine this peak and you have this anisotropic constant, okay, then it's a direct relationship. Okay, you have to do it. Let me show the presentation now. Okay, just 1 second. You will see more clearly. Oh, okay, there's someone sharing the screen, so I cannot do it right now. So basically, we have to go to this zero field proof.
Just a minute. I think Dr. Bernat, just a minute. Some participant is presenting. Please, Hidayatullah, please don't present.
Sorry?
Somebody, no, some participant is trying to present the screen. So, Hidayatullah, please.
Yeah, maybe the wrong person.
I think
you stop it.
Yeah.
Because I cannot do your presentation again.
Yeah. Just a minute. We will just stop.
Yeah.
Thank you. Yeah, thanks. Thank you. Yeah, now you can continue.
Let me share the screen again.
Yeah.
That is, this is the previous slide I showed you. Yeah. This is what I was mentioning. The volume of your particle, you have this anisotropic constant. If you know this anisotropic constant, then it's pretty easy, because this is a Boltzmann constant, okay? And we can determine this blocking temperature by the temperature where the zero field curve gets to the maximum. Okay. This temperature has something to do with when this permagnetic state is no longer stable. So it no longer keeps any kind of remnant or porosity. So this is related to the size of the particle and the volume, of course. So determining this blocking temperature means determining the volume. Okay. Of course, if you have some distribution, this will grow then. If you have less distribution on the volume, it will become narrower. Okay. So let me see if I can see more questions. Oh, yeah. 1 second. I need to scroll up. Anything. Yeah. There's another question that said, can we do BSM measurement option in PPMS? Yeah, yes, of course. The answer is yes. For example, in fact, the example I showed you is the BSM option which is present. It can be adapted to a PPMS as a plugin option. Yeah, this is in fact a BSM. You can convert your PPMS into a BSM system. Okay. Next one, how to find the maximum energy that's executed. Yeah, the MS to Z code, the part of the first monetization, there is an area, and which is related to this maximum intensity. And next question. Can we obtain field cool electrical core from magnetism? This is not something that we do. Of course, you could compare, because field cool is something to do with the fluid magnetization curve and the loop coming from the saturation. Basically, at low P, we are comparing both states of magnetization. Single field cool one has something to do with the fluid magnetization curve of an M versus A, and the field cool is the one coming from the more magnetized state. Yeah, you could do it, but it's very time consuming. It's much more easier to do this temperature dependence field cool, zero field cool. It's much easier. Next one. Sir, what's the best available material for magnetic applications at present? Well, there are many of them, but in terms of permanent magnet, the most powerful I've seen so far is these neodymium iron bore magnets. These are the most suitable for permanent magnet. Also, depending on what you want, for example, if what it concerns to magnetic shielding, for example, the new metal is the most commonly used because it has a high permeability. It's very useful for isolating zones where you don't want magnetic field to be present. It's very useful, for example, in our labs where we have the equipment quite close one to each other. We need to isolate what we call the side magnetic field. This is the residual magnetic field that is outside our system when we apply a magnetic field. If you isolate with these new metal plates, you're getting very well. Also, for example, you could imagine magnetic materials exhibiting also electrical properties, such as what we call magnetoresistance. In this case, now some magnetites, manganites are quite useful for that because they exhibit what we call this higher magnetoresistance behavior, which is a very huge effect on electrical resistance when change magnetic field, for example. That depends on what you want. Okay, so next one. Is there a difference you can observe when the shapes vary particles? Is there a difference you can observe? Well, with magnetometry, we cannot evaluate the effect of the shape of nanoparticles. Because this kind of magnetometry we do is what we call a macroscopic magnetometry. So we are counting everything. And the particular shape of each nanoparticle is something that the shape it would cause is not something that we can see in this kind of macroscopic measurements. With this, we should go to alternative technique like transmission electron microscopy, which will be the rest in this case. Next one will be simply how can we know about magnetic properties of nanomaterials before characterization? Well, normally before going into that characterization, for example, imagine that you are following some kind of research line. Normally, you know something about the material, or you know something about what you expect, and this is something that now you check when you do that characterization. This is how we normally work in this kind of material research labs. People have started searching into bladylography, and they know more or less what they want to get. Because with what you consider magnetic measurements, there's a broad map where you can start playing. You are in a certain certain conditions, for example, in temperature or magnetic field, and you have to move one or the other. It's good to know a little bit of your material before starting, because you have to choose whether to do a temperature dependence or a magnetic dependence. Okay. So next one, yeah, as I said before, can you see the screen?
Yeah, we can see.
Yeah. Again, you measure this zero field called temperature dependence. This is a black curve. Okay. Low temperature as you heat up, your particles start to get no magnetization. You have to remember you that this is a small power field, that the low temperature is not enough for fully magnetizing your particles. Okay, you'll have some appearance of some ferromagnetic domains inside it. As you increase the temperature, the effect of temperature will start to promote one domain respect to the others. This will cause an increase of magnetization. This will end to a limit where the size of the domain is equivalent to the volume of the particle. See, at this point, the ferromagnetic state will no longer be stable. This is when this is the blocking temperature. It is something that is related to the volume of your particle. Okay. So each volume corresponds to one blocking temperature. Okay. And I'll please answer the. Simply, how can we know about magnetic properties? I know. But this is what was already answered. Yeah, hysteresis loss in image curve. Yeah. Hysteresis, the presence of hysteresis loops in a ferromagnetic material is related to energy losses. Basically, the volume and flows by the hysteresis loop is away from finding this loss. Normally, hard magnets, those receiving high positivity, are those known to have huge magnetic losses when you cycle the field to positive to negative and back to positive. Yeah. This is related to the width of the hysteresis loop. Okay. Next one is, can we measure image data at high temperature more than 400 Kelvin per ms? Yes. The answer is yes if you are using this DSM open option. Basically, you place your sample on the top of a holder that includes a small heater. Okay. You place the sample inside your system, and you heat up the sample. You can do it up to 1000 Kelvin. Sample has to be small because the setup is rather small. It has to be very thin because since we are working a huge range of temperatures, you have to be you have to work with really small samples, so the sample follows the temperature response accordingly to the temperature change. And next one is, will a material have both superferromagnetism and superferromagnetism? Well, could be. Yes, some materials which are called multifunctional materials that basically their ferromagnetic properties have impact on the electrical property and inversely. So basically, you change the magnetic properties and the ferromagnetic properties, electrical properties change accordingly. So yes, this could be possible. That depends. That depends on the material. In fact, every material has its own world. Actually, when I go to characterization of sample, they ask me about material magnetic properties. Yeah, this is quite useful for people who work with magnetic characterization. As I said before, it's very difficult to us to decide what to measure when we know nothing about the material. Okay, we could start from a starting point of doing a temperature dependence and see what we have. But it's good to know what we should expect from material in order to make a more accurate measurement and to take more profit of the measurement time. We just consider that these magnetic measurements, especially the ones involving superconducting solenoids, time is money. The expenses of a measurement are relatively high because of that's because we are using helium for that. So knowing a few things about the material is very helpful for us in order to make a more accurate and useful measurement. Okay. Next one. Is there any link between magnetic property and thermoelectric property? Well, as far as my knowledge covers, this is something that is not very familiar to me. But again, my feeling is that that depends on the material. Cannot answer much precisely because this complete thing is not fully my field. Okay, so sorry for that. Next one. How we say that material processes para or permanentism for DSM analysis. Yeah, basically the DSM analysis gives you the magnetization of your material. You can change, for example, you can do a temperature dependence measurement, for example. And in the case of paramagnetism, you measure, for example, from 10 Kelvin to 300 Kelvin, and it's paramagnetic in all the range. You would see this inverse respect to temperature behavior. It's fully biased both. Whereas for the case of ferromagnetism, you have if you are far away in temperature from the purity temperature, you saturate your sample, you apply some fluid to do it, you start at low temperature, and you start heating up your sample while you measure. For example, with the DSM analysis. Okay? You'll get the several points at low temperature. The value of the magnetization will not change much. And as you approach to the purity temperature, the magnetization will drop very fast. And above the purity temperature, it will be up as a paramagnetic. Okay. But this can be done with DSM and with extraction method. You can choose the method you like. DSM analysis doesn't give special difference in this case. What about accuracy? I'm not sure about what it refers about accuracy. Can the person who asked this question to provide more information, please?
I think Dr. Pandin, if you I think what is the accuracy of the PMS and the VSM?
Okay. PPMS by itself has nothing to do with accuracy. DSM should be more indicated to compare the accuracy of the DSM system and PMS system. DSM system has a noise floor of 10 to the minus 6 MU, a low field, whereas in the case of NPMS system, the one with the split magnetometer, you have a higher accuracy, 10 to the minus 7 MU, if you are using this oscillatory motion. but it's really, the accuracy has more something to do, not by the way you move the sample, but the way you detect the signal generated at the source of the radiometer. Or whatever system, but it would include a DSM system. If you place, with your detection electronics, you have a squid device, you will have a very accurate measurements. For example, there are new magnetometers that are based on DSM system that the accuracy now is 10 to the minus 8 and called DC magnetometry. Okay? So the accuracy widely depends on the sum of the technical rules and the electronics that they are involved in your setup. Sure. Can you please share something about the regular transition? Well, at this moment I don't have it in home. Sorry. I should. The thing is that I'm not a Bozzo graphic access to the network.
That's fine. That's more specific question. That's an iron oxide. It's a metal insulator transition. Okay, yeah. That's fine. I can push to the next.
I don't have it in class.
Okay. Yes. We will switch to the next question.
Yeah. How to study the crystal structure of nanopermanent materials? Well, in this case, probably you would need a complementary technique that would be the use of X-ray diffraction. It would be the most appropriate one for the crystal structure. For what it concerns to magnetic materials, if you can orientate your crystal, all your nanocrystals in a single direction, all of them. For example, you could have a very nice study on the magnetic anisotropy. That would be a very nice study. But what it concerns the crystallographic structure, we need to this. Again, the same question about pure numbers groups. No, this was included before. Pure and zero are temperature dependent. This is the most simple way of getting them. With field dependent groups, yeah, that's what I said. It's not the best way for doing it. Please share the color point. Please share the physical link. Sure. Chromatic nature of a material will change with respect to the chemical synthesis. With respect to the chemical synthesis, reaction temperature or reaction. Let me read it again. Chromatic nature of change with respect to chemical synthesis, or reaction temperature or reaction time. Well,
he's asking, I think, whether the preparation method.
This is something that's more to do with the preparation than the magnetic measurement technique. We cannot answer.
Okay. Yes, we will move to the next.
Regarding room temperature, conductivity, the answer is not. There's not such a conductive material at room temperature. So far, any purification that has appeared so far is proven to be caused by some kind of measurement artifact. And it's something that is very important to know the measurement artifacts, because it can lead you to false conclusions. Especially if you are dealing with such very low magnetism signal measurements. Sometimes the appearance of any impurity in your holder or any non-well center or unprotected regulator lead you to very funny results. The spurious signals is something that we have to be taken very seriously. And I think that there's no more questions. This is very interesting. Actually, the magnetic correction. Okay, this diamagnetic effect appears mostly when you are measuring low signal samples and you're placing the samples, for example, intro on top of a cluster which is normally diamagnetic. When your magnetic film is saturated at high magnetic fields, you no longer have this. Let me show you and go back to this magnetic threshold. You don't no longer have this, but you have a negative slope event. In the case of if you have such a condition, it's very easy to subtract the magnetic pressure because you expect to have a ferromagnetic material already separated, so it should be through a flat line. If you don't have this, you have a different slope. You just determine this slope and you can just taking it out. Okay. Well, in the case of temperature dependence, magnetism is just an offset for the curve. In this case, it's a little bit more difficult to determine what should apply. The next, for the material measurement, we need to show this property. Good, yes, because the end-of-watch shape in the type 2 superconductivity are quite unique. For example, if you start from a zero field pole measurement for a superconductor, if you start applying magnetic field at the first glance, you will have the effect of the perfect diamagnetism. That will be a straight line with a negative slope until you reach the critical state of the superconductor. So this would give you the first clue. If your material would be a type 1 superconductor, you will have also this perfect diamagnetism. Yeah, it's a unique behavior. It's very difficult, very different to the one you would have for a permanent material, which would give you immediately a positive slope in the energy dependence. Okay. Sure, can superconductivity and permanentism coexist? In the beginning, it was not proven that they could exist. The thing is that one material being ferromagnetic, if you magnetize it in some way that can overcome the critical field of the superconducting phase, and this superconductivity can be destructive. So, in principle, it's difficult to imagine. Although there are some assemblies between ferromagnetic and superconductivity which are placed one next to the other that can definitely exist. That depends on the signal caused by each of the phases. Okay. One more question. In some samples, embassy zones are not closed after going from negative 2 to positive 1. There's a split at the end. That could be the reason. Yeah, I've seen this at some cases. This could be caused mainly because, for example, at the beginning and the end of the measurement, for example, if you have a huge temperature dependence on your sample, for example, and your system is not fully thermalized between the beginning and the end, you could see this dependence. Also, it could be by the cause of a small change of the geometry of the sample. I've seen this many times with powder samples. Probably during the measurement, for example, if the powder consists of nanoparticles, if you go into a cycle from positive to negative, from negative to positive, probably some of the particles are rotating. Probably part of the powder is changing in shape. In fact, it could give you some splitting. And also the source could be simply an accommodation of the thermalization of the system. Basically, this also happens when you change the temperature from room temperature to 10 Kelvin. You immediately measure the system components still shrink a little bit. That means that the shape of your folder, the shape of the sample chamber, or even the gradiometer can change a little bit, so it can fake the value of the magnetization. That could be a reason also. It has more something. You could find the source on anything that can drift over time, whatever it is. I think that there are no more questions.
Yeah, that's fine. I think that's very. Dr. Lakshmi Narasimhan, if you are there, you can interact directly. You can ask some questions.
Yeah.
So that's fine. That's okay. So thank you, Dr. Bernat, for your wonderful presentation. So it's excellent. It was an excellent presentation. Just a moment. Dr. Tamil Chelvi, are you there?
Yes, sir. Are you hearing me?
Yeah, that's fine. So I request Dr. Tamil Chelvi to give what of thanks for our speaker.
Thankful. First of all, I would like to thank our beloved principal for giving us an opportunity to conduct this webinar. On behalf of our management, beloved principal, HOD, and faculties of Science and Humanities, I would like to thank our honorable speaker, Dr. Bernat Bozzo Closas, for this wonderful speech on DC and AC magnetometers from basic principles to real examples. Your content today will be echoed in our mind for a long time to come. Thank you, sir. I would like to thank our participants for participating and being patient listener. I would like to extend my special thanks to the coordinator team for making this webinar session a great success. Once again, I thank all for your cordial cooperation. Thank you. Thank you, sir.
Thank you.
Thank you, ma'am. Thank you, Dr. Bernat. Just a request for the participants, you can participate tomorrow also. I welcome you all for tomorrow's presentation by Mr. Pondian on nanomagnetism for biomedical application. Thank you. Thank you, Bernat. Thank you, Dr. Bernat. That was a wonderful presentation. So we learned a lot about the instrumentation. So there are some students were also there. So undergrad students. So that was a wonderful presentation. So they learned a lot about